Starting in the supreme name of Almighty Allah. Thank you so much for joining the last lecture of the intelligent sensing and remote sensing. So as the course is finishing in the reverse order, like we started with the remote sensing, but we are finishing on the intelligent sensing as it is in the reverse order. This is the last glance of the whole lecture, and that is the advanced analysis in its application. The lecture is land cover classification, and this is really the longest lecture of among the whole lecture. So far we are covering almost, you can see 44 slides, but this is the mostly summarized form that I have tried among all of the lectures to be shortest. Further, let's start step by step the core concepts for the for presentation and revision. So this is like maybe some of stuff, not, I think so there is no repetition for the, I mean, for previous lectures, like we have seen only PCA in 7 also, and in the 8 lecture also PCT. Then that in PCT in the 8 lecture was in more detail as comparison to the 7 principal component transform. What is land cover classification? Uh, Let me tell you in brief. The whole idea of this lecture is that we would like to make this whole remote sensing data to map them thematically. It has been started very long ago based on the classical classifiers or classical or traditional ML. The whole idea is that one, the digital map we are now seeing in the more visualized or attractive visuals, it is just due to these classifications that we gonna make the output more visual and attractive. And the idea is to express the information on a precise location. That is the whole idea. Classification means assigning each portion of the Earth surface to a class. Like on the Earth surface, we have multiple areas like rivers, water and rivers, although one thing, but we can see vegetation, forests, many things, residential blocks, commercial areas. So we're going to try to put these areas into a single class. So on Earth surface, we are having this kind of existing things. So we're going to have a predefined class, and we will try to put all of them in a certain class, what thing is belongs to what class. So a class is a homogeneous category selected for a defined set. As I said, this will be predefined sets such as the water, vegetation, the urban area, or soil, agriculture, forest. The output of classification is a thematic map. That is the key objective of this whole lecture. Also, as I said in the start of the this lecture, we're gonna make a final output to be presented our whole pixel or observed data on a map, and it should be accurately and precisely represented. The core idea satellite data becomes useful when pixels or regions are assigned meaningfully land cover classes. Yeah, that is the main objective. Otherwise, the remote sensor data will not make really sense. If the pixels or the regions which we have observed or sensed, if it is not placed correctly in the land surface, so it will be really not making sense the effort we have done so far. What is classifier? So classifier is the operational block that assign land cover classes to each classification unit from the input Earth observation dataset. Actually, in this classifier, it is the broader version of the classification unit. The exact job is done by the classification unit, but the classifier can have multiple classification units. A classifier is the operational block. See, and they further discussing that assigns the land cover classes. The land cover classes are predefined. We have seen like water, vegetations, urban areas, soil, and many more. Okay, that assigns land cover classes to each classification unit. So this is important. Here we have the top classification unit. We will discuss them furthermore. So each classification unit from the input Earth observation dataset. So the exact job the land cover class is to each classification unit from the Earth observation data set. When we are giving an input data sets to the classification algorithm, they are trying to the classifier exactly which is an operational black. The assigns the land cover classes to each classification unit from the input observation data. So input data is remote sensing data, which we have already applied some of the data corrections, basic analysis, and all this stuff, and it's ready for further processing or analysis, like advanced analysis. Processing classifiers applies rules or learned patterns. Yeah, exactly. The classifier will be already trained on a certain data. Now, in this case, when we gonna give the new data or test data to the classifier, so they will compare according to certain rules and learned patterns. The output is a thematic map. The simple idea of the classifier is this, that the classifier converts Earth observation data into a map of classes. So on the map, if we look into detail, we are looking into multiple objects on the Earth, like as I said, vegetation, urban areas, soil, water, and many things. So the classifier main idea is that they want to convert the Earth observation data into a map of classes, a map with a multiple classes, and it is exactly what we are looking at the map. So they have multiple classes for the land cover objects or shapes, anything. So they are trying to put the exact pixel values on the exact class. This is the job of the classifier, which is an operational block. We will further see the classification unit also. What is land cover and land use? In short terms, the land cover is the biophysical covers of the earth surface. Example, vegetation, water, asphalt bed, and bare soil. So land cover is actually, you can consider, naturally it is covered with pre-built in stuff, like as you see, vegetation, water, asphalt beds, bare soils. But the land use is the exactly human usage of the earth surface. That area which are in the human usage, it starts from the parking areas, roads, commercial areas, residential blocks, in the agriculture fields. So this is the a little bit differentiation of the land use and the land cover. So important distinction again, land cover is what physically covers the surface. Physically mean in terms of like, you can assume a natural, the physical word here. So land use is how humans use that surfaces. So where the human involvement is coming to exist, and this is called land use. Although human is everywhere, but we have separated this like by land use and land cover. So in the land use, if you see that the parking areas, roads, residential zones, so here the majority in the crowd of the humans are a little high as compared to like rural areas of forest and all these area in mountains and waters. That's how we are differentiating land covers and land use. Remote sensing is generally more directed to land cover than land use. That is obvious because the part where humans are living is not that much. And we are dealing in the remote sensing more or less the land the land cover. Although we are also dealing the land use, it's not something, but it is more directed with the land cover because satellites observe physical surfaces properties, and that is obvious. Although if you look into the case of the land cover and land use, we are also looking for the asset pits, okay, roads or something like that. So exactly, if we can look that, that's also physical, and both of them are physical shapes and structures or natural stuff. All the roads are very big, and there is same residential blocks are also very big. So because the satellite observe the physical surface properties, so they will also they will also observe the physical surfaces of the land use also. But in terms of the space they have covered and the land cover, it's much more than as the human. That's why the statement is a little bit correct in terms of that. We have certain types of classifications like hard versus fuzzy classification. So the hard classification, each pixel belongs to one and only one class. This is exactly the fuzzy rule. So if you assign them in the traditional way, like clear, crisp cut, you should have to say one and only, one or no, or one or zero. Like one means to this class, or zero means no, not this class. So exactly the same hard is exactly like it's no or exactly. This is how we are putting the class of fuzzy classification here, and we are also using the membership value. If you see the hard classification means belongs to one in only one class. That's mean the hard here means one here. So pixel, for example, pixel equals to forest, pixel equals to either water, pixel equal to urban. So certain pixel at the same time can be only belong to one class, either water, forest, or soil or urban areas. But fuzzy or soft classification, uh, we are also calling the soft and like hard or fuzzy. We also call the fuzzy soft. And why soft? Because a pixel value can belong partially to several classes. And if it comes, then we have a membership value for that. Like if you see a single pixel can belongs to 60% of to vegetation, 30% soil, and 10% urban. And this is also really helpful in the remote sensing. It is exactly assigning the overlapping, and we can see in the core idea the hard classification gives one final label, while fuzzy classification gives membership values for multiple classes. And this is obvious that we are having overlapping of the pixels, so it is really helping the fuzzy or the soft classification. As I said initially, that the classifier is the operational block of the classifier is the operational block that assigns lane cover classes to each classification unit. The lane cover classes are assigned to each classification unit from the operational block, and for what? From the input or the observation data set. Now here, like classification unit is a part of the classifier. A classification unit is the portion of the dataset on which one class decision is made. So actually here the decision is making like the input sense data is now belong to which class. It can be a single pixel, a group of pixel. Sorry. It can be a single pixel, a group of pixels, or segmented region or a super pixel. If we go look at again into the classification or classifier or in more detail, the classifier is say it is an operational block. So the operational block can have a multiple classification unit. And what is the job that assigned lane cover classes? So in the classifier, we are having multiple lane cover classes, and they are assigning each classification unit. Each classification unit, let's suppose we have a one classification unit for the water, let's suppose from the input observation dataset. So now we are having with the classifier is having the earth and earth observation input data, and they have a multiple classifier. The classifier have a multiple classification unit. In one of the classification unit is about the water. So if the earth observation data is matching the water, so the land cover, the water classes will be that will be assigned to the water class. So this is how exactly how exactly classifier is working. So we can say that the classification in the classifier, the classification unit is a part of the classifier. And here exactly the classifier is doing the same thing, but the exact decision is made inside the classification unit because the classification unit have the class. A classification unit is the portion of the data set. It is a portion of the data set on which one class decision is made. Okay, we have a whole data set, okay, of the earth observation data of multiple pixel values or super pixel values, different things, or it could be the object or spatial information. So when it is given to a classifier, so the data set is now grouped into the multiple classes, or it is divided into multiple classes. This is why because the classifier is looking to the data where this pixel is belong. So they are taking that pixel and putting in the classes. So this is how the data set on which one class decision is made here. So it can be single pixel, like it can be group of pixels, or segmented region, as I said, like as a superpixel. Superpixel is in simple terms an object or a shape. Pixel-based classification is quite common, but object or superpixel, as I said, like superpixel is object-based classification may be more useful when spatial resolution is high. So when we are looking into the data, if the data have a higher spatial resolution, and we already discussed such kind of trade-offs before in the multiple lectures, so then we can also look into the object or the shape-based classification. The core idea is the classifier does not always classify individual pixels, and it may classify meaningful regions also. In why this is happening exactly, if you look into the individual pixels is accurately assigned to classes, so it can definitely classify the regions pretty well also. Similarity based classification, this is very obvious, like in spatial continuity, if you remember, this is more important to study. Classification is often based on the idea that each class has a typical behavior. Like typical behavior could be due to the water has a low reflectance in infrared. So this is obvious, like they are understanding from the patterns of the such kind of classes. Like during the training, the class in the classification, the classifier is learning how certain class is grouped, or what kind of feature certain class has. So this is the main thing. If we look into the second example, like vegetation has a near infrared reflectance, high near infrared reflectance due to the leaf structure. We already discussed this many times. Build-up areas may have a strong short-wave infrared response. This is how we are differentiating, or the build-up area class have a typical behavior. And if you look into the vegetation, it have a high reflectance in the near infrared reflectance. So the vegetation class is based on this typical behavior, and the same is going for the water, which has a low reflectance in near infrared, because that is absorbed. So the classifier translate this typical behavior into mathematical rules or decision rules. And this is how the classifier is taking a decision. Inside the classifier, classification unit is making a decision about a certain pixel, either it belongs to which class. Important warning is that in theory, every material could be detected by its specific spectral behavior. So far, we understood theoretically that every material could be detected by its spectral response, but in reality, classes may overlap. That could happen many times, and the reason is that it is obvious that it could be detected the same electromagnetic waves that can overlap with each other. This could be one of the reasons that the neighboring pixel values may be nearby up and down. So therefore, we must check class separability. That is really important. So class should be separated very clear, crisp cut. So while we are assigning the data based on its typical behavior, it should be very clear and obvious. So theoretically, we understood that the material could be detected by its specific spectral behavior, but there is a chances of the class overlapping. And that's why we introduced the soft membership, like we have seen soft classification or fuzzy classification, which has a membership value. So that is really helping us to avoid a little bit the overlapping. Training and ground truth, this is really important. We can say this is a reference data. Its mean is reliable information about the actual class of the classification unit. So we said that the single classification unit is the part of the classifier which has the which is about a single class, and they are assigning a data set into multiple classes as per the pixel values. So what is exactly training in the ground truth? Like here we are discussing mainly the ground truth, then the training. The ground truth is we are actually collecting under the surveys or the direct knowledge and the visual interpretation, independent reference maps, what exactly this class should be made of. Like the information should be reliable, because this is the reference data we are comparing later on the training data, or we are testing on it. So it could be used like for both reasons. So the class we are making, it should be on obvious and clear information. Training means using ground truth or drive classification criteria. So here the training means is using ground truths. What do you mean by that? A sensor, let's suppose, observed a certain data, and we train a model on that, and later on we can check on this ground truths also again. And this is how exactly in the training we are using to check, cross check with this ground truths, that they what the drive classification criteria is meaningful or no. The core idea is here the classifier learns class behaviors from reliable reference examples. So this is really important. Initially, the classifier is trained on real and reference data. Then next time when we are observing data using the satellite, and those data from the Earth observation is given to this classifier, and they are assigning the pixel values into the multiple classes. So that's why the training should be done on a good and proper and authentic, reliable data, because otherwise that will be too much optimistic decision we are making about the classification. We have certain types of classification, and we will discuss its sample, some of the models in detail. Supervised versus unsupervised learning. In supervised learning, uses labels training data. You can call them, the main idea is the knowledge driven. In unsupervised, the group data by similarity without labels. That's why we discuss similarity based classification. So similarity based classification is helping out in the unsupervised learning. In the main idea is it is a data driven. The above one is knowledge driven, because we already know about the certain class, and it's a class is predefined based on the pre existing surveys and prior knowledge and independent maps. So this is the idea. In the supervised classification, classes are predefined, as I said. So we know this is the class, and this is the typical behavior of the class. In the classifier, when have a new data and input or earth observation data, so they are just comparing the classifier according to the each classification unit. This pixel value belongs to which class. This is the simple idea. The classifier learns to recognize from training examples. Exactly, in the training they are learning from those. And unsupervised classification, pixels are grouped by natural similarity. This is really important, by similarity based classification. Here the model is looking into learn from the exact input data by its similarity. The resulting groups are anonymous at first. When this unsupervised operation is happening, so initially the groups are anonymous. I mean, they don't have any name, or that is not for sure confirmed to be as a class or no. It is moving further on, or scanning or classifying further data. So after that, the classes can be confirmed and must be labeled later. They are labeling the letter because initially they are looking for its similarity based classification or pixel values. The core differences is like supervised is we tell the classifier the classes before training. Exactly, like before to training we have classes. In the data they know before training on a certain data about the classes. So these are the classes I need to learn from the data and to assign them. This is the whole idea in the supervised learning. But in the unsupervised learning, the classification groups similar pixels first. So they are taking the similars pixel first, then we label them afterward. So this is the main difference you can consider between both of them. Now, as we already discussed about the classifier, now in supervised classifier is like the general idea we know about the classifier, like it's an operational block. But for supervised classifier, it is a classification. For supervised classification, the training example must be selected on the image. So what do you mean by that? The training set must be representative of each class, large enough and reliable, perfect, preferably not only from one connected area. The core area poor training data leads to poor classification, even if the classifier is advanced. This whole lecture is discussing about the same thing we have seen, like the training example must be selected on the image. In the data should be enough large to train the classifier on that. Otherwise, if our classifier on a certain data is quite advanced, and if they don't know about the data more, so after that, if we classify new data, so there is a chances of mistake. So the data should be like, you can see the representative, like the training set must be representative of each class. On amount of data on which we are training the certain supervised classifier, those data should represent the all of the classes. Otherwise, if it's not in the training, and next time when they have certain types of pixels, so they may assign to the wrong class. There is a chances. That's why in the core idea we have written that the poor training data means like one of the reason if we don't have enough amount of data or not enough huge to poor classification. In what is the impact of the poor classification? It will be even if in the classifier is advanced, but the new Earth observation data cannot be classified pretty well. That's the main reason. Unsupervised classification. Now we are slowly discussing the. We have only discussed here the supervised classifier, but now we are discussing unsupervised classification a little bit in more detail. Unsupervised classification uses a little or no prior information. Pixels are self-grouped by similarity, so they are trying to group a similarity-based pixels. The output is usually spectral classes. Yeah, they are giving you still the output responses as spectral classes. You're like putting them all again in the spectral classes. Okay, which later must be matched with the meaningful information classes. Okay, when we collect based on the unsupervised learning or a data driven certain classes, then we are also confirming those with the or matching with the meaningful classes information. For example, like spectral cluster one is one, maybe water. This is like a class assigned by the unsupervised classification. They say, okay, maybe two is for the agriculture, maybe three is for the rock. But after this classification, we are confirming them, you can say, or we are matching them, that this classification has been made by the unsupervised learning, or this class has been made based on these pixels. Either it is correct or not. That is the whole idea. Spectral classes and real information classes may not match perfectly. This is the chances the actual class or the predefined, not a big comparing with the predefined, but the ground truth should be compared with the unsupervised classified class. That is for sure. And this is in the important issue we are writing. It's not necessary to be perfect. There is a chances of error. So far, what was happening before the supervised or non-supervised, or the in the classification, or before not existing of the modern algorithms or most advanced algorithms, how the classical classifier was working. Classical classifiers are based on the regular statistical assumptions. They are mostly using the Gaussian fitting or the Gaussian distribution, or they are often assuming the normal the data. So they were using the Gaussian class distribution. We already discussed the Gaussian distribution in the lecture 7, if I'm not wrong. like a bill shape curve, and this is most important, like in the statistical assumption. Unsupervised classifier, a classical classifier, how the unsupervised classifier was working. They were mostly using the k-means or kappa means, iteratively adjust the classes centers and reassign pixels until it's stable. So this is the main idea how the unsupervised classical classifier was working on which method. One of them is the key method, like we discussed. They were adjusting the class centers, sorry, and reassign the pixels until it's stable. So this is how the unsupervised was working, looking into multiple pixel values for the class center. So until they are finding the proper values to become this class more stable, or they were not until they were able to find the enough amount of pixels to stable the class. ESO data is similar to the k-means but can merge and split the classes. This was the main thing. Initially, they were doing like the k-mean, iteratively adjust the classes, class centers, or reassign the pixel until it's stable. But when it's becoming a stable, then they were looking into the classes or the collected pixels. Is there any chance for the further classes? So this is they were merging them, splitting them the classes. And in the supervised classifier, a classical classifier, we were using like a parallel piped, using values range for each class. So for certain class, we were using, okay, these are the values, and if it comes the pixel in this values, it will be assigned to this one. So this is why called parallel piped. And we were using the minimum distance, like assign the pixels to the nearest class centers. This is how the minimum distance is working. Let's suppose if an pixel is near in terms of the value to the one which we already assigned, so they were trying to put them the next value, pixel value, in that one same class. So this is called the minimum distance. And the maximum likelihood, like using the Gaussian probability model for the each class, which is not always fit. So this is one of the case. We already discussed this information of the Gaussian distribution and Gaussian fitting on a histogram and all these things. Core idea, like the classical classifier works well when classes have a simple and regular statistical behavior. But in real time, it's not all the time the case that the classical classifier work, because the condition can be changed, and classes can have a not simple details in regular statistical behavior. It can be very, very dynamic and change. So that's why the need of the other things come into existence, like why machine learning is needed. So in many real world applications or problems, classes behavior is not simple, as I discussed. So why the class behavior is not simple? The first thing is the complex shape distribution. That's really important. Gaussian distribution is not enough anymore. Multimodal classes, high dimensional data, as we are collecting multiple bands of the data. So in non-linear class boundaries, that's really important. Well, sorry, overlapping spectral response. That's another important aspect, because spectral response is a mostly wavelength dependent. So in changing of the wavelength dependent, if we are collecting the responses and its spectral response is changing in terms of the values of the pixels in the form of the vectors. So it is really important, and these are the complexities we were facing. The class behavior is not normal or simple. In machine learning is useful because it can handle the complex class boundaries without strict Gaussian assumption. This is the whole idea why the machine learning is coming into the picture. Machine learning and land cover classification, that is the main application. Machine learning can be applied to the Earth observation data for classification. And it is usually supervised, yeah, because we know about the classes, our classes are predefined, meaning it depends upon the training levels. Common examples are of the machine learning in the remote or the land cover classification, which is usually, as I said, it is a supervised classification. And the reason of behind that is we are predefining the classes. So we want to check and compare. So the examples of the machine learning in the land cover classification are the decision tree, random forest, and support vector machine. And the core idea is email classifier can solve difficult classification problems, but they depend strongly on a good large training data set. The important thing is the larger data set or the huger data set we have, the more good result we will have. Or the machine learning classification will work, supervised classification work more better. And the reason is pretty simple, because from the multiple data set or the huge data set, they in the machine learning we are learning from the data more, more texture, information, ages, everything. So that is why it is important the data hugeness or increasing of the data size. We are starting with the decision tree. A decision tree is a supervised classifier. This is coming under the supervised classification. It's using trees. So the tree structure, they are having internal nodes. So the internal nodes is representing the features or the bands, and the branches are the decision rule. In each branch, they are having certain decision. In the leaf, we are having the final class outcome. Either this value will be assigned weird. So in the initial we have seen that they are having the feature or band. So let's suppose we are assuming this is our band or it is our feature we are looking, and it's the data is given into the decision tree. As we are coming from the top of the node, internal node, which is exactly the feature or band, then on the branches we are having the rule. Okay, here the rule is this one. If that rule is matching, so this should go this side or either this side. So then we are leaving to the leaves at the end. So at the in the leaves, the final decision is make about the class. Okay, this will to this one class. So this is the idea of the decision rule, how it's working. Example, for example, if the band is greater than the certain threshold in the leaves, in the branches, we have the conditions or rules, or the decision rules, we can say. So the threshold will decide go right. If it is less than, it will be go left. And final leave gives the class label. So the final leaves are deciding the class label for the certain pixel value, but they have some benefits, like it's more intuitive, so it really makes sense, easy to explain, and it's robust to missing data in data issues. If the data have some certain problems, no assumption about the distribution here is made, but they can have a cons because it can overfit. That's the that's the main issue of the decision tree. They are overfitting here, and mainly due to the dealing with the missing data and data issues. So they are trying to overfit here. The core idea is the decision tree is classifies by a sequence of a symbol decision. That is the idea of the how decision tree is working. The decision is very simple rules, like if in condition, if else condition. We are now looking into the random forest, which is the second class mission supervised classification method. Random forest tree is the in symbols of mini decision tree. So as from the name is pretty simple, random forests. So far we were having only the decision tree. Now we are having multiple decision tree, and it's called random forest. As from the name is a little bit obvious. And each tree gives a decision, in the final class is chosen by majority voting. That's really important. So multiple trees are initially deciding about a certain pixel, but after that they are looking by the voting for the majority, voting like which what is the voting for which class. The boots, here we are defining like how the random forest reduce overfitting by using mini trees. And so that's why the data is not overfit anymore. Bootstrapping, or random features selection. We will discuss all of these many trees or number of trees in the machine learning or in the random forest and later on. Bootstrapping is discussed here. Bootstrapping means randomly selecting training sample with the replacement. This is really important, like the samples are selected randomly with the replacement, and they are consistently trying to replace the the sampling for the decision rules. So random feature selection, this is the third one. If you look into random feature selection, is each tree uses a random subset of features. So it's not that like in the feature selection or the random feature selection we are having only one, but it's a subset of features making trees less correlated. So the correlation is here almost you can see null, or they would like try to make them irrelevant with each other, because if it is making so the decision will be made ambiguous here in this case. So pros, more accurate than the single tree. Why? Because they are reducing overfitting by using of the mini trees, bootstrapping, and random feature selection. This random feature selection is really amazing. Like they are trying to make the trees less correlated, because if a certain tree is related, so related in terms of with each other, so the decision will be a little bit ambiguous, and the voting will be going to most of those are related uh, trees, because the related trees will select the related decision by the leaves. So in the final outcome or voting, we will see that it's going to that one class, but in actually it will not be. That's the main features they are using to overcome the fitting, overfitting here by using the mini trees and random feature selection in bootstrapping. Okay, bootstrapping is exactly like selecting the training samples with replacement, like they're trying to consistently replace a training sample, more accurate than the single decision tree and reduce your overfitting. Trees can run in parallel and very effective for the land cover classification. This random forest is really effective, but they have some cons also. At the same time, they are increasing their complexity and not ideal for the hyperdimensional data set. And the reason for the hyperdimensional data set is due to the high dimensions of the data. And as we have seen here, the complexity is already increasing, so it will be too much tough. Random forest is one of the main ML workhorse for the land cover classification. It should be taken into account that it's still one of the main method. Number of trees in the random forest. We have seen that many trees. So now we're looking into the number of trees in the forest. The number of trees is a classification parameters. So this is exactly the number of trees is acting like classification parameters. So based on these number of trees working or acting as an parameters for taking the decision, the more parameters you are having or more trees, so they will accurately identify a certain pixel value for overcoming the overfitting. Increasing trees usually improving performance at the first. Why? But after a point, improving become a small. Exactly. And the reason is also obvious. There is no more change coming due to increasing the parameters. And by a number of trees, this decision has been made and it's voted by many trees that it belongs to this class. So if we increase more, automatically we are increasing the computation cost. So computational cost keep increasing. That's one important point, because if you want to confirm ourselves more with the multiple parameters, like multiple parameters, you can check out the classification parameters or trees. So increasing those already means increasing the computation cost. Adding more trees may not improve accuracy. Yeah, it's also obvious, because it will be decided by many number of trees that, okay, this pixel value is decided by this. So the voting of the majority will be going to for that one class. The core idea, more trees helps to a limit Yeah, they will help to up to some limit. After that, they mainly increase the computation. And if we are increasing the computation, mean automatically increasing the cost. Support vector machine SVM is again uh, a machine learning method for the classification, supervised classification, and it finds an optimal boundary between the classes. So they are actually looking between the two classes for the optimal boundary. In two dimension, this boundary is aligned in two-dimensional data, but if it is going to the higher dimensions, then it's called hyperplane. So they are looking mainly for the, sorry, for the two different classes. And the best hyperplane is the one with the maximum margin between the classes. So when we are having the maximum margin between the classes, that is the best hyperplane. And hyperplane is using a multiple dimension. And it's really good for the hyperspectral and ultraspectral or multispectral data. Support vectors is exactly are the data points closest to the boundary. Support vectors, so they define the class separation mainly, and what kernel does or window if a classes cannot be separated linearly. So SVM can use a kernel to transform the data into space where separation becomes easier. And that's a really important point. Another one in kernels or windows, and they have some pros and cons also. Effective in the max in the high dimensional spaces, as I said, it's in the first, like for the multispectral response in the ultraspectral response data, they have multiple bands with the less narrow micrometer distance data into the space where separation, strong wind classes are clearly separable, and they will really help you with the classes are more separable. We are taking already in the supervised predefined classes. So if you're using SVM and the classes are well defined, so it will be more strong for that case. And it is already obvious the method of the classification, supervised classification. The cons are unsuitable for very large and large data set. As the data set is increasing, so the kernel rules will be like separated by, okay, in the kernel we discussed that if classes cannot be separated linearly, so SVM can use a kernels or a window to transform the data into a space where separation become possible. And case if the large data set and where we have the high dimensional spaces, in just for the non-linearity case, I mean, like the classes cannot be separated linearly. So SVM will try to put them into space and use the kernel to transform them to become easier the separation. That's why it's really difficult. Insensitive to noise also, and it's choosing a kernel can be difficult. Exactly, I already explained the kernel selection. SVM tries to find the cleanest separation boundary between the classes. So this is really important. They are looking exactly for the boundary between the classes. As I said, in the multi or the higher dimensional data, it's called hyperplane, but in the two dimension, it is called a line. So based on a line, they are differentiating the classes, its typical behaviors. Main issue with the traditional email. What is happening with the traditional email and why we are looking into the deep learning? Traditional email relies mainly on a pixel-based spectral information. Yeah, we are discussing since the long. To aid the spatial information, okay, if we are increasing the spatial information and the spatial resolution is very good, human must manually design features such as the texture, indices, object shapes, neighborhood statistic. And this is really important. So that's the main issue if we are having high spatial resolution data, and for the training of SVM or the random forest or the decision tree based algorithms, they will not be really effective. So this is called the feature engineering. In the core issue, ML can be powerful, but it is often needs human design feature to understand the spatial context. So for understanding of the spatial context, the ML or the main issue with the traditional MLs comes into the picture, and we are going into the deep learning from here. Deep learning is also the subset of the machine learning, but using a multi-layer network, neural network. So compared with the traditional ML, deep learning can learn features automatically, and the machine learning uses algorithms to learn from the data and often needs handcrafted features. But in the deep learning, learns through the deep neural network and can learn hierarchical features from the raw pixels. So they are learning from the raw pixels even. So that's why here we don't need to manually or by hand draw the designs or shapes and objects for the spatial information in case if it is like high resolution needs more label data and in computational power. That's obvious because they are using uh, a multiple neural network or multi-layer neural network. So this is obvious they will need more label data and high computational power. That's really important. The core idea is like learning shifts from feature engineering to feature learning here. So for we were doing the feature engineering like uh, removing or taking the features from the data using by the traditional method. But here now it's really important becoming from that the feature learning. Based on the feature learning, we are introducing the spatial information in the thematic map. In the main objective is thematic map generation. The feature engineering versus feature learning. In short terms, the humans design features manually in the feature engineering, like in DVI indices. We have discussed this one. Like I still remember, in these are some of the indexes we have seen, like matrices, like as for the assessment of this different types of the objects on the earth. We have seen NDBI also, MNDB, MNDWI also, which was the modified natural difference of water index. NDBI was the normalized difference build-up area, uh, build-up area index. B was stand for the build-up exactly. NNDVI is normalized difference vegetation index, textures, band ratios, and the shape features. But in the feature learning, they are learning from the raw pixels we have discussed. The model learns user features automatically from the data. And this is really helping for the spatial information. This is common in deep learning because they are learning from the useful features automatically from the data from the raw material, the raw pixels. Core idea deep learning can learn about spectral and spatial patterns directly from the data. So far we were discussing the, if you look into the issues with the main issues with the traditional ML, like the traditional ML is realizing mainly on the pixel-based spectral information. And that's why to aid the spatial information, so human need to do these things manually, but it is really difficult for even the training perspective. So it can be different any time in different cases. But here, this feature learning makes this easy in using the deep learning. The models uses useful features automatically from the data. Sorry. So this is quite common in the deep learning. And the core idea is the deep learning can learn about the spectral and spatial directly from the data. So based on the deep learning of the concept of the feature learning, we are learning directly from the data about the spatial information and the spectral information, both of them. And this is why the issue with the main traditional ML was not supposed to address these things. The need of the deep learning and the feature learning comes into the existence. Classical ML versus deep learning or machine learning. Classical machine learning versus deep learning. So the classical method was like assuming the strict, often like Gaussian. Okay. In machine learning, we are comparing the classical method before even the machine learning. Machine learning and deep learning, these are the three methods compared here: classical, ML, and versus deep learning. And there is another ML versus is missing VS. So classes methods assumption, it is like strict, often Gaussian. In the machine learning, it's still assumption is flexible. In the deep learning, it's totally data driven because they are learning from the data directly. Feature extraction was raw bands or a simple stats. In the classical methods, in the machine learning, it is handcrafted features. Why handcrafted? We discussed already, because for the, especially in the machine learning or the supervised case, we are using supervised. That should need to be designed for the first time for the by hands, from which the machine need to learn. Then the input earth observation data will be analyzed, that they are assigning well or no. And what about the feature extraction? It's automatic and hierarchical in the deep learning. In the computational, okay, spatial context in the classical method is none. There is no concept of the spatial information, but about in the machine learning, it was a moderate. It was not that much, or you can say limited or engineered. In the case of the spatial context of the deep learning, it's really high because they are learning both the spectral and spatial information directly from the data. Even here, we are overriding the ML in terms of supervised classification to learn about the spectral responses, because there was the need of the manual designing of the or by hand or handcrafted features. Computational cost of the classical method was very low, but in the computational cost of the machine learning, it was moderate. But it is really obvious the cost of the computational will be very high because they need to use a neural engine, and they need a more high computational hardwares. So interpretability is very high for the classical methods, but for the machine learning, it's moderate. In even in the deep learning, it's quite low because it's complex. That's why. Okay, now discussing the neural network classifiers. What is neural network classifiers? Are based on the artificial versions of the human neurons, and they are flexible, computationally heavy, and powerful for the complex classification problems, independent on the large tag data set when supervised. So we need supervisor is really dependent on large data sets which is tagged. Deep learning become powerful because neural networks can learn complex representation. That is the main idea, and this is how the neural network classifier works. In the neural network classifier, it is a mimicry of the human neurons, and they are really super flexible. Computationally is very heavy and powerful for the complex classification problems also. That's why we are here for the spatial information analysis also. Uh, then we are discussing the convolutional neural network, CNN. The convolutional neural networks are very popular in the computer vision, in the earth observation data analysis. CNNs learns from the hierarchical features. We already discussed this. They are learning directly from the data, even from the raw pixels. In the previous comparison, if we see, even we have written here that they are learning automatic. So you don't need to be very specific for that. So the convolutional neural networks early layers detect the simple patterns such as the ages. The early layers of the neural networks, they are learning about like ages, boundaries. In deep layers detect the textures and shapes as you're moving inside the layers, and later layers detect the objects and land cover patterns. And as they are going more in deep and they are looking into the texture and patterns, and these informations are helping for the spatial information or analysis. The core idea students learns from the local spatial patterns and combines them into the higher level features. That's the core idea. CNNs and remote sensing now. We are taking into the remote sensing data. Standard computer vision usually works with three RGB channels like RGB or red, green, blue. Remote sensing data is more complex because it may include the spatial dimension. Like there is not only one dimension. Okay, so this is how like it works with the traditional or the usually work with these RGB channels of images. But in the remote sensing, we are having a more complex data, or complex because it may include the spatial dimension, width and height. If it is the spatial, because they will have width and height. In the spectral information, many bands we are having here. So it is even becoming vectors. So temporal dimension of the time series analysis or stacks. So therefore, CNN and remote sensing may use a 3D or a 4D structure due to the multiple dimensions of the data and the 3D or 4D structures with the convolution across the spectral and temporal dimension. They will have a separate convolutional layer for the spectral and temporal dimensions specifically for these two. If you see in the temporal, we are having multiple data of multiple times. So this is becoming very high, and that's why they are assigning a separate convolutional layer for the temporal and spectral. And spectral information is important, having multiple vectors in there. Now we are looking into the hybrid CNNs. The hybrid CNNs uses the 3D convolutional layers to extract the spectral features. So this is really important. The as we discussed initially, the CNN is helping, or the deep learning is helping in the spectral and the spatial both information. So here the hybrid CNN is exactly looking into this same problem, the 3D convolutional layers to extract the spatiospectral features. So this is including both of them, then reshape into the 2D layers for the final classification. And this balance is accuracy in the computational efficiency. But the core idea here is the hybrid CNNs are useful when data contains both spatial and spectral in structure. We said we have both. So if the spectral information, spatial information is high, it means spectral is also very good at the same time. So this is really helping like when the data contains both at the same time. Now, what is receptive field? A receptive field is the field in the region of the original input image that influence one neuron or a pixels in a given neural network. So you can assume like an outlier. It is causing or influencing in the image a neuron from the image. They are influencing the neuron or one pixel in a given neural network. So it controls how much context the network sees. So this is really important, and we are looking into it that based on that one value which is influencing the neuron, or based on the pixels which they are available in the given neural network layer. So it is exactly controlled that the looking of the network layers. So a small receptor fields captured local details. So this means they are looking into the local details, and the network looking is not really far. But a large receptor fields captures broader context. This is really important. In CNNs, receptor fields can depends on the pooling layers, strides, and convolutional depth. So these are the main three things in more technical term when we are implementing the CNN. So we are using in the use of the convolutional method or the class. Like what is the pooling layers and strides in the convolutional depth. So this is mainly the receptive field is dependent on these things and how they are influencing in the image. A neuron or a single pixel can affect the neural networks for the maximum looking of the whole network. So the core area receptor field determines how much special context is used for the classification. Exactly, that's really helping in this way, in the idea and the conceptually, that is the meaning. They are determining in how, because of the input image influence, or one neuron, or one pixel. That pixel could be maximum, let's suppose. So they are reflecting exactly in the output, and they will show you the influence. And if it is high, let's suppose the receptor field is high, so they are covering more information. They are not only looking into the local details, or minimum details. So the core idea is like, they are determining how much spatial context is here is used, because in the spatial context it is really important to understand about the neighboring. So pixels as are continuous, they are looking into it. All these pixels by themselves are discrete, but as we said that looking into the neighboring, it means automatically increasing the distance. So distance increasing means they will have a direction automatically. So based on these things, so they are also looking into the neighbor. So if you're looking into the neighbor, so this is automatically reflecting the spatial information. So we can say the larger receptive fields mean the higher concept, the higher spatial context is used for the classification. Problem with the standard CNNs. So we discussed the CNNs and what is wrong with the CNN. In simple term, they are giving you an output as in a single layer of the image. So standard CNNs like these are the predefined or pre-trained models like ResNet or VVG were originally designed for the image level classifications based on the standard CNNs. The output, one label for the whole image. So one label for the whole image. In but Earth observation, we usually need a full thematic map. That's the main idea with the full or the standard CNNs, not a single label. So the core issue here is the image level classification destroys the spatial information. So we need a spatial information here, while the Earth observation needs pixel values, or the object level maps. Even pixel level is not maybe needed anymore for the correct boundaries and determining the administrative boundaries or regions. So even the object level maps are needed. So although the output is a one label for a whole image here in the standard CNN, so we're addressing this with the fully convolutional neural network. So fully connected neural networks, or FCN, um, solve this by removing the fully connected layer. So like the classified deep features map initially, then they upsampling the predictions back into the original image size, upsampling prediction. So which is the sample they are upping back and it's predicted into the original image size in the fully convolutional neural network, or you can call fully convolutional networks. The output a classification for every pixel now, because they use the classifies the deep details of the map or features of the map, then the upsampling the prediction back into the original image size, and output is for the each and every one pixels values. This is called semantic segmentation. And based on this, we are identifying the object. And FSN provides pixel-wise classification map instead of a one label for the whole image. But we will still facing an issue with the FCN again. So now we are having an issue with the fully convolutional neural networks, or we can call them like fully convolutional networks. Like FSN goes to the pooling layer, which reduce the resolution. We have since tried pooling. Uh, sorry, we have seen the CNNs is receptive fields depend exactly on the pooling layers tried in convolutional depth. So we are again looking into the FSN. We are having an issue with the or problem with the FSN. So the network understand what is present exactly here if it's in go through the pooling layers. So pooling layers and a layer inside the convolutional layer network, fully convolutional layer network based on which they are deciding the class, which reduce the spatial resolution here. So this means the network understands what is present in but loses the precise location detail. They are looking into the existence of the pixel, but about forgetting about the precise location details. So FCN, the fully convolutional network output may lack up sharp boundaries, and sharp boundary is really important for as for the administrative purposes or for the identification of the proper thematic map. So FCN have a stronger semantic context but weak spatial details. And the ultimate goal is we are looking into the spatiospectral response. And that's why unit is introducing. In the unit, we have solving this problem by encoder and decoder structure. The encoder is the connecting path or the contracting path. It applies the convolutions and poolings and reduce the spatial size and increase the feature depth. Initially, we are looking for the features like boundaries, edges, and all these things, and captures the deep semantic context. But after the semantic context capturing and increasing the feature depth and decreasing or reducing the spatial size, the decoder is the expanding path now. That is contracting and this is the expanding. It upsamples back the original image size. The same it has been done by the FCN, like fully convolutional network. We have seen the method of the fully convolutional network upsample the prediction backs to original image size. Exactly, this is the expanding of the decoder, the unit depending or expanding part of the decoder. It upsamples back to the original image size and it restored the spatial resolution because it was reduced in the encoder because it was contracting or interacting with the first. So gradually reduce the feature channel here, and it is increasing its the spatial information here. So the core idea is the unit combines the deep understanding with spatial detail to produce the accurate maps. This is the most workhorse of the AI or the AI used in the remote sensing so far. And the unit is the deep understanding with the spatial detail to produce the accurate, because in the decode or the expanding part we have seen, they are generally reducing the feature channel here. That's the whole idea. Skip connection is a skip connection connects the encoder layers to the decoder layer and at the same spatial level, because we reduce the size in the encoder and increasing the spatial information back. If we see gradually reduce the feature channel here and we are restoring the spatial resolution here, over there we reduce the spatial size. So the SCAP connection is connecting both back to the spatial levels. So they pass high resolution details directly across the network. That's really important. They help the network know what the object is and preserve where the object boundary is. This is really important information we needed for the spatial information or spatial analysis. Draw sharper edges. So the edges are the sharp in preserve where the object boundary is. Let's suppose a certain building is, so they can precisely identify for you using the unit skip connection while they are connecting the encoder and decoder with the special layers, because in one layer we are reducing the size, in the other one we are decreasing the sizes of the spatial information. So they know about first of all what the object is, and the boundaries are preserved in sharper the edges are the. So examples for the building, like let's suppose deep features identify the object as a building, while shallow features preserve sharp roof corners. So this is exactly the differences of the skip connection they are doing in multiple cases. In the first case, like in normal illuminated time, so maybe the features identify the object as a building. Clear. While shallow features preserve the sharp corners of roofs. So this is the main and core idea of this one. The skip connection preserve the final spatial boundaries while keep deep semantic information. They are also keeping at the same time the deep semantic information. Unit as a workhorse for the AI based mapping. We discussed this is really important AI concept for the remote sensing or the thematic or AI based mapping. Unit is important in that observation because it works well with the smaller level data sets and it preserves the boundaries and it is stronger for the semantic segmentation and it is useful for the building extraction, parcel mapping, road mapping, and damage assessment. It's even helping in the post in pre assessment of the area for the damage in the core area. Unit is one of the most important deep learning architecture for pixel-wise land cover mapping. Pixel-wise working and not object-wise here. But automatically they are giving you the spatial information, so it is also possible to be work object-based. This is the damage assessment with the unit. Unit can be used for binary classification, such as a building or a non-building. But if we compare the same case for the classification or binary classification of the unit, we can find them like pre and the post event of the buildings maps. So damage can be detected by the extracting the building pixels before the event and extracting the building pixels after the event. So we can compare the maps. So this is identify the damage or missing building areas. Pretty simple and easy. And we can see the diagrams below. The diagram value here is on the top going on after the assessment, the damage assessment with the unit. And the other way it is going downside. So I mean there is a missing values. And this is exactly they are representing the damage over the unit. This is really important in advance. The contextual classification, modern AI is redefining what context mean. So context is no longer only local neighboring information like for the spatial case. The new methods are introduced for this, like some of them are the video transfer graph neural networks or multi-scale models. So the vision transform, they divide the image into the patches and learn how pages are related globally. This is the method they are using for the contextual classification, not only based on the neighboring information. So graph neural network is they use the objects or superpixel as a node and model relationship between them. That is really amazing, and that's why it's called the graph neural network. So they are using the single objects or superpixels as a single node, and after that they are making the relationship among the nodes, and this is how the graph neural network is working. For example, a building near a parking lot. So in this case, if you look into the building as in a node, and we draw in making parking and node a single, and we draw its relationship, so they will understand the context more pretty well, not based only simple on the neighboring information. Multi-scale model, they combine local and global information such as the age of a road or road inside. Okay, so the multi-scale model is exactly they are combining the local in the global information, such as the age of a road and the road inside a suburban neighborhood. What does it mean? In the multi-scale model, if we know about the ages of the road or the road ages, so road inside the suburban neighborhood, so they can still identify better due to the multi-scale model status. So the core idea is the modern classification method try to understand both local details and broader context. And this is really important for the advanced analysis of the contextual analysis also. So for the neighboring information is really helpful. So they are still using the local details, but looking into the broader context also. Result assessment, one of the important part, we have done classification so far, we need to confirm them or its reliability. So accuracy assessment compares the classification maps, ground references data, our test set. So we have already discussed about the ground truths for reference data. So the test set shows not overlap with the training set. That is really important, and it should be a very optimistic result. We have already discussed this. The accuracy will not be that much very good. It can be pessimistic again. So the core idea classification maybe is not complete until its accuracy is assessed, and it should be assessed with a new fresh test data set. Okay, now we are discussing the ground truth and test set again. What is it that like for the accuracy assessment? Ground truth is a reliable information we already discussed from the survey, and about the actual land cover. It's coming from the training or accuracy assessment. This is mainly used for the ground truth, which is coming from the reliable information about the land cover. We discussed the reliable information such as the surveys or independent maps in the uses of the ground truth and testers for the training or accuracy assessment. That is the main objective. And the test set is the portion of the ground truth used only for evaluation, because here we are evaluating the pre-trained model and look into that how it is working. They are classifying the new earth observation data correctly or not. And why it should be based on the ground truth, because the more the data realistic for the on what they have trained, so they should have to predict them very well. In the new earth observation data, which is a, you can say raw more, so they can be defined or identified them very well because of the understanding on the real training of the ground truth data. Important requirement statistically is significant. We are looking for that it should be representative of the whole classes, separate from the training data. That's a really important point. It should be not the thing which we have trained, and based on the training data we are again evaluating them. Confusion matrix is compares the class labels with the actual ground truth labels. So what is the class labels and classified labels? We, let's suppose we have already classified labels with the actual ground truth classes. What we have predefined classes and what is the classified labels. This is the same. We are comparing them both. So in the rows of the confusion matrix, it is usually assigning the class, and in the columns classes, we are having the actual ground truth classes. So main diagonal is usually representing the correctly classified samples or pixel values, or the off diagonal, it's all of them all by error. So the core idea of the confusion metric is shows which classes were correctly classified and which classes were confused. This is really important, and based on the confusion metric, we are looking into the multiple details, multiple more accuracy assessment methods or assessment methods. Here, these two are really important concepts of the omission and the commission errors. In simple terms, it's more interrelated, but they have a minor difference. Like the first one, we need to understand them with a more precision or details, because omission means omitting. Commission means we are committing them. So in the omission error is a pixel belongs to a class but was classified as another class. So in this case, we know about the pixel. This pixel belongs to the soil class, let's suppose. But the only mistake is happened here. It is assigned to the random, the another class. So it is a mistake. Example, actual forest classified as agriculture. So the omission error is exactly related to the procedures or the uh, procedures accuracy, which is recall. Now let's discuss the commission error. Or in short, more short term, if I say the omission error is here we are making mistake. Okay, like mistake means we don't know about that. Or in the commission error, a pixel is assigned to a class. Okay, it looks like the reverse order of the omission error, but does not actually belongs to that class. It means they're also misclassified. The opposite example of the above one, like actual forest classified as as a agriculture, but here agriculture classified as a forest. If you see here, this is a little bit different. Over there, actual forest. The actual was the forest, but they considered as a or classified as agriculture, the actual thing. Here, agriculture classified as a forest. Now, this is exactly two main different things. And even it's in the opposite since they are going. Here, it is the agriculture is not actual because here we are failing to do the right thing. This is the main thing. Over there, we are doing wrong thing totally. Here we are failing to do the right thing. It means we do not have the ability to correctly identify this thing. Both kind of thing, either the agriculture classified as a forest is correct or no, or agriculture is an actual or no, and what we are classifying. So this is why it's called commission error. So this commission error is related to the user's accuracy or precision. So see, this is now more giving detail about as the above one is recalling. Okay, it is the actual forest classified as an agriculture, but here agriculture is classified as a forest. So the above one, the omission errors, the procedures accuracy or recall, and the commission errors are the accuracy, the precision, like the user's accuracy, like precisions. Okay, we will discussing these more further. Also, these recall and precision. Now, one of them from the confusion metric we can find is overall accuracy, but the overall accuracy is mainly discussing like the ratio of the correctly classified, which is in the diagonal to the total number of pixels. So we divide by them and it's the overall accuracy, and here is the formula also. And from that we can find a percentages, divide, multiply by 100. So it uses the diagonal of the confusion matrix only. So the core idea is like general measures of classification correctness, but it does not show the which specific classes are problematic here. So one of the general parameter we are deriving from the confusion matrix. Now we are discussing the producer's accuracy or the user's accuracy. Like producer's accuracy is the recalling and the user's accuracy is precision. Out of all actual of a class, now these things will more have to omission and commission error. If you look into the producer's accuracy or the recall accuracy, out of all actual pixels of a class, out of all actual pixels of a class. So we have a class. In that class, it is the actual class. Okay. How many did the classifier find them? Like from the actual class, find them, you can say learn them from them. Okay. So it is measuring the omission errors, because what is actually learned from the actual pixels of a class, so they will find that exactly the same thing. So that's why this is the omission error. We are omitting this thing. Omitting means removing this thing totally. In the user's accuracy or precision, and if you see the procedures accuracy recall, so I mean recall the memory, what you learned and what you are classifying, and how many did the classifier find them from the actual class. So if they find accurately in assigning the wrong number, so a wrong class, it is the omission error. In the opposite, the user's accuracy or precision, now it's a discussion of the precision out of all pixel labeled as a class. Now, if you think it to this one, it's a little bit difference with the above one. Out of all actual classes, pixels of a class label of a class, but here they are discussing out of all pixels labeled as a class. Like we label them as a class. You take an example of unsupervised learning, which is data driven. Okay, out of all pixels, we label them as a class. How many are actual that classes? Now we are looking into this class, okay, which we label them as a class and looking into the how many are the actual belongs to that class. From the actual class what we are having and what we label them as a class, how many of them is belonging to them. We labeled a class and we have the actual class and we are looking into the how many are the actual of that classes. So this is like precision, here the main thing we discussed, we are making as a class, or you can assume like uh, already predefined class could be possible in this example also, but in the unsupervised example, it's really more makes sense this thing like as an example because it's the more data driven. So we are initially having anonymous classes, then we are labeling, but it could be possible to be pre-labeled in the supervised learning case. So it is like the opposite of the procedures accuracy and recall. Again, in that one, we are looking out of all actual pixels of a class. Okay, there is a single class in the heaven actual values of the pixel values. We are looking into the how many did the classified is finding from them. So this is recalling, and this is measures of the omission error. How many we are them removing from them, because if we find, let's suppose we have the actual pixels of a class, let's suppose 100 number, 100 pixel values, in the classifier is finding 90, so it means they omitted the 10. So this is called the recall error. In the user's accuracy or the precisions, out of all pixels labeled as a class, let's suppose we have a class in the same case above one and it's labeled as a class, let's suppose, how many are actual that classes. Now we are looking into the class labeled as, okay, how many are belongs to this class. Now this is commission. So from the word commission you can understand we are giving them a concession, so we are failing to do here. So it is measures the commission error here, like the out of all pixels labeled as a class, we are looking into the how many are the actual belongs to that class. Here we are going like as an example, we say half empty or half full glass. That is exactly the same example, more matching here. They are looking into the different thing, but it is, you can say that they are measuring two different types of errors from different perspectives. So the core idea is the recall focuses on the mixed pixels. That is obvious, mixed pixels. And the precision focuses on wrongly included pixels. Here we discussed here in the previous of the commission error. Here we are actually failing to do the right thing. So exactly they say the precision is focused on the wrongly included pixels, but in the recall focus is on the mixed pixels of the actual classes in the classified classes. Here we were doing the exactly wrong thing. We are confusing them. In the precision case, we are doing totally failing to do it the right thing. Even the right is really far, even we are doing totally wrong thing. But in the precise case, recall case, we are maxing them. We know about, okay, this is the actual label, this is the actual pixels of a class, but the classifier is classified as wrongly. That is the main reason. We discussed this in more detail, and it was really important concept of that one. And I told you this will be the longer session, but we're almost at the end. And kappa coefficient is one of the most important thing in this assessments also, and it's usually used in the remote sensing. Kappa coefficient accounts for the agreement that could happen by random chances. So they are looking something into the chances more. So by default, the K coefficient, also called people, accounts mainly for the agreement that could happen by random chances. So they say it is account for the random chances, but this is important because some some correct classification can occur by pure chance also. So kappa compares the observed agreement, what is observed, in what is the chance agreement. So they are looking or taking into account these two things, what is observed and what are the chances of that one. So let's suppose from the data we observe this one in or it's already pre-defined classes or data set for the evaluation or for the assessment, and this is the chance agreement. Let's suppose it's coming certain thing, then we are comparing both them and we are finding the k or kappa coefficients. So kappa gives a fair accuracy measures than the overall accuracy. We told initially that the overall accuracy is mainly looking into the correctly classified out of the total. So it's a general assessment of the data. But over there, we really don't know about the problematic ones and where the problem is exactly coming from. So here, if we look into the, although the modern AI workflows often uses other measures too, it's not necessary like to using only the kappa coefficients or the oral accuracy and the commission errors, commission errors, and the user's accuracy. User's accuracy exactly means the precision, and the producer accuracy exactly like recall. One of them is addressing the producer accuracy. Recall is addressing the omission error or measuring the omission error. In the user's accuracy or the precision is measuring the commissioner. Not all by these things, but they are using more than from this, so to find the exact thing. But the kappa gives a fair accuracy measures than the overall accuracy. That's confirmed. One of them is really famous. It's called IO or Jacquard index. IO is exactly the meaning is intersection or union. It is widely used in the semantic segmentation, so it measures the spatial overlap between the predicted mask and the ground truth mask. So we have two different masks, and they are looking into this overlapping. In the simple formula, if you look into the intersection or union, area of overlap. So let's suppose there is an area they are overlapping in area of a union. So that's why it's called intersection or union or a Jacquard index for simple terms, GI. So this area we are having where this is overlapping, okay, and at a certain place there is a union. So dividing the overlapping by the union, so it becomes the intersection or union. And the core idea is the more demanding than the sample accuracy, it measures the special bit more especially. That's why, and if we look into the our case, we were looking for the spatial reflectance response or this kind of analysis more. So for that one to address the special fit more, for the assessment after the classification performed, like many operations we have discussed under the class supervised classification or non-supervised classification, decision tree or random forest SVM. Then we discussed the issues with the traditional ML. We discussed the neural networks classifier. Then we discussed fully connected neural classifier FCN. convolutional neural network. There was an issue with that one. Then we discussed the fully convolutional neural network. We went from that even to the unit and all of these things. So for both of them classification methods, this one is really helping as that to understand about this spatial fit more. This is the last one. It's really important. It is F1 score. If one score is, let's suppose we have used the to measure the omission error in the commission error by the precision in recall. Commission error is measured by the precision in the omission errors by the recall. So they are looking into the harmonic mean of the precision in recall. It balances how many correctly object or pixel were found. So they look into that how many pixels are found correctly or objects, but on the other side, how many predicted pixels were actually correct. Like let's suppose we used by the classifier and predicted how many numbers of pixels or object correctly, and they compare or balance this with how many correct objects were found. One of them is the correct objects were found, or it is one of them is predicted. This is totally different. So the predicted thing is compared with the, you can say with the existing or the ground truth in a simple, more simple terms to say. So how many correct objects or pixels were found? So we are looking initially to the number of pixels or objects correctly found like on a diagonal. If you take an example, how many predicted pixels, or you can say here an objects were actually corrected. So the prediction can also be wrong. So we are actually matching these two, which is correctly found, and it is exactly correctly, but there is a predicted or classified, and we are also chances of not exactly. So they are keeping the F1 score, the harmonic of these two, of the recall and precision, the main score, which is also representing about a good assessment. And we are usually using the F1 is useful when focusing on a specific class, like such as building, roads, floods areas, or damaged area. So if one scores balance false positive and false negative, this is really important, and this is all the time off diagonal. So this is what we were discussing, like in the above case of the balancing, it's more now representing very good the core idea for the class of interest. Like we know on the confusion matrix in the diagonal, they are the true false and true negative. But in the case of the off diagonal, they are false positive or false negative. So this is exactly we are looking, and they are exactly representing the same thing, like how many correct objects or pixels were found, and they are exactly correct in this case, okay? Like in the actual cases. So also looking for the predicted pixels were classified actual correct, and it can be also not actual correct. So they are keeping the harmonic balance of these two, or in more short term, the precision and recall. Precision is working on the commission error measuring, and the recall is measuring the omission error, which is really, really minor. You can say not a minor, but understanding this is more conceptually of the omission and commission on the precision in both of these, and then if we understood that one pretty well, so if one score is pretty simple, they are keeping the harmonic of these two in reflecting the a mean. Have you seen the harmonic mean of these two? So this was the last lecture, as we said, and it's quite long if you look into, and as I was also sometimes sneezing and feeling differently because it's quite long session of a 2 hours, and hopefully you like it, and it is really tried to make this complex stuff more simplified in the short words in the content of this slides were also very simple to put into them. Yeah, looks maybe not more mathematically heavy. Yeah, one thing myself I noticed to be more good in terms of infographics, like graphs is really helping. Hopefully you like it. See you maybe in the next some of the course. For now, bye. See you.